Hey everyone, I'm Pete, and I'm talking about the cryptographic coprocessor. This is a nifty little chip here that can do digital signatures. A lot of times when you hear the word cryptography, people immediately jump to encrypting data and decrypting data. Well, this chip actually focuses on authentication. So it can create a digital signature, and then it can also verify that digital signature. And this is actually really useful when you have a mesh system of sensors or any kind of IoT device reporting data. Before you send that data, you can use this to create a digital signature, and then you would send that data and the signature home, and then at home I can actually verify that. And so then I know that the data coming to me from that sensor is in fact from that sensor and nowhere else in the world, and that it didn't get messed with. There was no middleman attack changing my data. I want to highlight that the configuration on this is a little tricky, and so it actually has 128 registers to mess with, and that affects how it works. So we created a very simple, easy to use configuration sketch. And so you can run that sketch, get it configured, and be up and running really quickly. But if you want to do some of the more advanced features with this, or something different like the Diffie-Hellman key exchange, going beyond signing data and verifying data, then you may need to do your own configuration. So we're going to jump into some specs on this, and then we're going to actually walk through all 6 examples in the Arduino library. So this Breakout features the microchip ATECC508A, the I2C version of that. So it has 2 Qwiic connectors, and you're able to put it into any Qwiic ecosystem. It is capable of doing elliptical curve cryptography. So it can actually create private and public key pairs for you and store them securely on its EEPROM. It can create 64-byte digital signatures on 32 bytes of message data. It's capable of doing the elliptical curve Diffie-Hellman algorithm, so it can create secret key on a public channel. It also has the standard hash-based challenge response protocol SHA-256 algorithm. And lastly, it has internal high-quality FIPS random number generator. So this is a bit more robust than the random number generator you get when you use a standard Arduino. It meets some higher standards put out by NIST and guarantees a really random number. All right, so we're going to jump right into example 1, configuration. It's sort of the first thing you have to do to this chip before you can do any of the fun stuff. So I've actually just got a single Qwiic connector going from my Artemis board here straight to the coprocessor. And I got a USB to my computer, and that's basically all the setup I had to do this first example. So I'm going to upload configuration. So just click the upload there. Nice, that went nice and quick. And then when I open my serial monitor, I get some information about the chip. So it first woke up, and then it tried to talk to this guy, and it looked like it did talk to it pretty good. It got the serial number back from it, and it also got a rev number, which is programmed at the factory. But if you look at this other part of it, the configuration zone, the data zone, and the data slot 0 are all not locked at this point. So it's a totally fresh chip. And what we need to do is actually do a bunch of configuration and tell it to create a key. And lucky for us, all we have to do is actually type a Y in this serial prompt, and then it will do all that for us. If you read all the readout here, it says, would you like to configure your cryptographic coprocessor with SparkFun standard settings, yes or no? And so I'm going to type a yes. Below that, there's a warning. It says, note, this is permanent and cannot be changed later. If you want to do this, type an N or unplug. So I do want to do this. I'm going to type a Y. Bam. All right, and then look at all the success messages I see. It looks like it wrote the config, it locked the config, it told it to create a key, that worked. It locked the data zone, and then it locked data slot 0, and it said configuration done. So this thing is ready to rock. And now when you look at the readout I got here, I get that same serial number, and then I get the version, but everything is locked up. And now it gives me another piece of information, which is pretty interesting. It says this device's public key. And so that right there is 64 bytes of data, which is a public key that is unique to this guy. And it actually created a private key and a public key when we did this configuration, and we'll never know the private key. That was created internally and then locked up, and you can never read from it. And that's the sort of security feature of this chip, is that we can read the public key all day and pass that around, but the private key is very much secure in the hardware on this chip. So now let's jump into example 2 and do some data signing. All right, so I'm actually going to pull up example 2 from the library. So you just come down to the bottom of this, my installed libraries. The example 2 is called sign. And so in this example, we are going to actually just sign a chunk of data. And then in the serial monitor, it's going to print out that signature for us, which is kind of the first step in understanding how all this works. So in my sketch here at the top, I have an array called message, and it's just 32 bytes of data. This could actually be anything we wanted, but for the example, it's just the numbers 0 through 32. And then let's upload this to my Artemis. So zippy, love it. Then I'm going to open my serial monitor, and this is very similar to the first example. Actually, all of these will initially try to talk to the chip and print out the serial number and the status of the locks on all the zones. So I can see that this chip has already been configured. I'm good to go. It also tells me my public key. And then the next part is the fun stuff for this example. So it shows me the message that I just signed right here. And then below that, I have my signature. And so that's 64 bytes of data that is my digital signature that could only be created using this chip. And I want to mention that it is using the private key right now to create that signature. Some other fun facts about this signature is that if I were to run this again, so if I hit reset on my Artemis, I actually get a brand new signature. Wait a second. It's the same chunk of data and the same private key, same board, everything, but it's different. That's something kind of unique with elliptical curve cryptography. Every signature I create, even if it's the same message, is going to be different because there's a little bit of randomness added into the math that goes on there. So I like to highlight that. And so let's jump into example 3 next and actually verify this signature. So I'm going to pull up example 3 from the libraries right here down at the bottom of my list. But I am also going to leave 2 up, because this one is actually got a little extra step in it. Before, in example 2, I mentioned that that digital signature we saw was created using the private key on this. If I want to verify, I need to actually use the public key. So that's how this sort of authentication cycle works. You would sign some data using the private key, and then you would verify it using the public key. And when we first configured this, we actually told it to create a key pair. So right now it has a key pair on it, a private and a public that are kind of mated together for life. And they work together in this way. So we sign with the private and we verify with the public. And so what I need to do is actually use the serial message I received from example 2, where I grabbed that public key, and then paste it into the sketch of example 3. So I'm going to do that right now. I've got my 2 sketches up. Let's go ahead and go to the serial prompt again. And I'm just actually going to highlight the text in the serial monitor right here. And in order to copy this from the serial monitor, you have to do Control-C. Just a little tip there. Won't let you right-click. And then let's jump over to this one. And I'm going to go to the top of the sketch for example 3. And you'll actually notice that I've got some placeholders in the example, because we need to know the public key, we also need to know the message, and we need to know the signature. And we're going to send all 3 of those things to the chip, and it's going to verify that everything's good to go. So in my serial monitor here, before I only copied the public key, I actually need to copy all 3 of these things. So I'm going to grab all 3, copy that, come over to example 3, and then I'm just going to actually highlight these placeholders and then paste in the good stuff. And then I also want to mention you got to rename this to public key external, because we are telling it an external public key. And we'll go ahead and upload this. Nice, that worked pretty good. Let's open up the serial monitor. Let's go and clear that. Why is that? Still got some stuff. There we go, there's a fresh response. So at the bottom of this readout, you can see success. Signature verified. That's pretty cool. It's kind of like the blink LED when you're first getting into cryptography. But what I want to highlight here is that if a single bit not even a byte. Like if the single bit in any one of these 3 chunks of data is changed, then it's not going to verify. And I want to show that real quick because it's kind of fun. I'm actually going to go to my message, and I think I'm going to change the very last bit. It was an F, and now I'm going to change it to an E. And now I'm going to upload this, and I'm hoping that it will fail. Let's see here, bring me that. Bam, verification failure. All I did was change 1 bit. Yes, that's so cool. That means that my message is totally intact, and that if anything gets changed at all in that message, then it's going to fail verification. So that's pretty fun. And the only place in the world that I could ever create that signature was using the private key on this chip. So that's verification in a nutshell. And the next thing we're going to do is example 4. Yes. And that involves Alice and Bob. So let's jump right into that. So example 4 actually requires 2 complete setups. And one is going to be named Alice, and one is going to be named Bob. And the point of this system is to show how a completely separate system, Alice, can have a chunk of data, sign it, and then send it to another system, Bob, and then Bob can use a separate coprocessor to verify that message. And so what we've done in the Arduino library is actually created 2 example sketches. They're both named example 4, but one is named example 4 Alice, and one is named example 4 Bob. So what you need to do is get these sketches onto each Arduino, and then you can start sending data between each other and see that Bob is able to verify Alice's message. So the first step we actually need to do is, in order for Bob to verify a message from Alice, he needs her public key. So what I'm going to do is actually upload this sketch to Alice and then watch her serial prompt here. So in this window here, I just saw my usual message saying this chip is good to go, it's been configured. And it also printed out this nice array right here that says Alice's public key. So I'm going to go ahead and Control-C that, copy it, go over to Bob's sketch, and at the very top of this sketch here, there's a placeholder in the sketch that comes with the library. It's just a bunch of zeros. I'm going to highlight that and then paste in Alice's public key. So now I'm going to upload this to Bob. And what we do here is we actually just open up another terminal talking to Bob. So I'm going to put him on the right side. And so you can see in the terminal messages, they look very similar. You've got your serial number from the chip, and those are unique now because I'm using 2 different things. And Alice over here says, "Hi, I'm Alice. Would you like to send me would you like me to send a signed message to Bob via my TX1 pin?" And so I've got TX1 here wired over to RX1 here on Bob. And I'm going to say, "Yes, please do that." So I type a Y. And then over here, Bob's terminal just heard that message. It received all 32 bytes of that message and the signature that we created. And then it sent it to the coprocessor, and the coprocessor said, everything's good to go. So at the end of this message here on Bob's terminal, I can say, "Success, signature verified." So let's jump into the next example, which is actually just creating random numbers, and we only need 1 board for that. And this example actually works very similar to the random example that you find for the standard Arduino random function that's built into it. But it can do a little bit more than that, and it actually has a bit higher standards in terms of how it creates that random number. Let's upload this sketch. And basically, this sketch opens this terminal prompt, and you can just see random numbers being printed every second, which is identical to how the random example works in the Arduino library. But you're actually getting a couple different types of random data. We have it set up so that it spits out 1 random number between 0 and 100 as an example. You can set those min and max. The next one is 4 to 500. But then you can actually have it create a whole integer's worth of random data. So you can just pull a random int. You can also pull a random byte and a random long. But then the really fun stuff is when you want to get 32 bytes of random data. So you can actually use the function here in the sketch. Let me get there. It does update random 32 bytes, and then it calls a global variable within the instance. And so you're able to actually get 32 bytes of nice, really good random data all in one call. So that's pretty much how the random works. We're going to use that in example 6, so let's jump right into there. So for example 6, it's very similar to how example 4 worked, where we need to have two systems talking to each other. And this is actually going to demonstrate how to do a challenge and response between two systems. This is really nice because if you have Alice trying to send a message to Bob, she could just go ahead and send that message with a signature. That'd be great. Bob could verify it on the other end. But what if somebody intercepted that message and then decided to send it later? That would be a pretty insecure situation, right? So what you can do is actually have Bob send a challenge to Alice that is a nice random number. We just talked about creating random numbers, right? So Bob's going to create 32 bytes of random data, send it to Alice, and say, hey, Alice, will you sign this? And then Alice signs it and sends it back. And then he knows that it came from her. And he can also say, you know, after 10 milliseconds, I'm not going to accept that signature that you just sent me because I have the random token that I just sent you. And that's going to expire in 10 milliseconds or whatever. So it adds this extra level of security to know that nobody intercepted your message. And that's pretty fun for a lot of reasons. But I like to highlight there's been a pretty cool hack that I read about while I was researching this project about breaking into people's garage doors, where it did just that, right? You send your authenticated signed message, but somebody can actually grab that message and then jam the system, and then you send another one, they grab that, jam the system, and now they're one step ahead of you every time you unlock your garage door. And it seems like it's working great for you, but then whenever they want, they can come and actually unlock your garage door. So having this challenge and then a timeout involved actually eliminates that ability to hack your system. So that's exactly what I'm going to be doing with this, is redoing my garage door opener. So let's jump into example 6 and show how this challenge will work. So Alice is actually going to initiate the conversation and say, hey Bob, I'm here, and will you send me a challenge data to sign? The other thing we need is one more piece of hardware. So in order for Alice to hear that back, she needs to have her RX pin connected to Bob's TX pin. So let's go ahead and upload Alice. And again, in order for Bob to verify that signature when she finally sends the token and the signature, he needs to know her public key. So I'm going to open up a serial prompt on Alice, and I'm going to grab her public key, so copy that, and then paste that into the top of Bob's sketch. Right now it's all zeros, just a placeholder in there. And let's go ahead and upload Bob's sketch. And then open up a terminal. And so you see Alice is on the left here, and it says, hi, I'm Alice, would you like me to request a new token from Bob? Yes or no? And then Bob's terminal over here, he says, hi, I'm Bob, I'm listening for incoming messages from Alice. Cool. So I'm going to type a yes into Alice's, and you can see that, I don't know if you caught it there, but there was some RX and TX going on. Actually, that was all happening on the RX1 and TX1 pins, which don't have any LEDs, but the serial prompt stuff is blinking. So it says, okay, sending request token now. So she sends that, and then Bob creates that random token, sends it to Alice, and she creates a signature on that. And at the very end of all this, Bob's serial terminal here says, success, signature verified. So that whole challenge and response exchange just happened, and we're doing it with 64 byte signatures. So this stuff is pretty hard to recreate without this chip and without this exact private key. So it's a really high level of security for that. So that shows example 6, which is getting into some pretty advanced, like highly secure stuff. So that was a pretty good run through of all the examples in the Arduino library. I want to mention that you can get a lot done with just one of these coprocessors. Examples 1, 2, and 3, and 5 can all be done with just one, and that'll get you signing data and verifying data. But then in order to do a communication between two systems, it's a good idea to have 2 of these chips, so you can pick up 2 of the coprocessors. Examples 4 and 6 show how that's pretty useful. I also want to mention that we did these with a hardwired connection between Alice and Bob, but that connection, that communication channel could actually be anything. It could be a wireless communication. It could be going through the internet with a client and server. And Alice and Bob could actually be anything you wanted. It could be the node on your IoT system or a controller for another system. And this authentication process can be very useful in lots of different ways. And I'm pretty excited to actually install one for my garage door opener. All it's going to do is be a button, but I will know that it came from that controller, you know? So that's pretty fun to think that that high level of authentication can come in a DIY project. So yeah, I recommend hitting up SparkFun.com and reading through the hookup guide and pick up one or two of these coprocessors. Hey, I'm Pete, and I am talking about, I like saying hey everybody, something cooler. It does something different. You're gonna have lots of bloopers for this one. And I'm talking about the, God, I can't even pick it up now. So that was a pretty quick rundown through, one more time. That was pretty good. I think I covered it all.